Alright, so welcome to this lecture in CM361, Environmental Chemistry, and I'm lecturer Dr. Fong. Today we'll be speaking about the topic that's imminent, emergent, urgent, that's called climate change. Right, and this relates to two goals of the United Nations SDG, Sustainable Development Goals, number 7, affordable and clean energy, and number 13, climate action. I'd like to start with a quote by our Prime Minister, our current Prime Minister, Mr. Lee Hsien Loong, when he addressed the United Nations Climate Ambition Summit to commemorate the 5th anniversary of the Paris Agreement on 12 December 2020. That was during the COVID times. He said, "Climate change is an existential threat for all of us, but especially for a small island state like Singapore. This global challenge requires a global response." What does it mean? It means that all of us have a part to play. It is on us, our owners, to act in every single way to combat climate change. So wait, what is climate change? We hear about it so often on the newspaper, in our textbook, even in this lecture. Now just briefly, let's try to rewind the clock and look at climate change as it is when we first encountered this term. Maybe a question is like, what's the difference between weather and climate? Okay, so we start to break it down first without the change. Okay, change is always constant. Now, climate describes an area's long-term atmospheric conditions and is governed by mostly 4 pillars: temperature, how hot the environment is; precipitation, how wet the environment is; wind, right, the movement of air due to pressure change; humidity, the suspended wetness in the atmosphere. Okay, so this weather specifies the conditions over hours or days. It's the duration, okay, shorter period of time. But climate summarizes the conditions over years, decades, and centuries. Years, right, 365 days, 366 days, decades, 10 years, centuries, 100 years, and so on and so forth. Okay. Look at it from the time frame per se, because the days are long, but the years are fast. That's the saying. Okay, so to read more about it, you can go back to our text for reference. Now, let's first start by look at climate change. Right, we associate this term climate change with the world is getting hotter, the Earth's getting warmer. Right, we look at something that's very fundamental in science. That's the energy balance. You learn in physical chemistry or in the past about enthalpy change. Every single reaction, normally there's an exchange of heat. So you know that the source of energy in the world comes from the sun. So in the sun, we experience this incoming solar radiations, right? And the Earth typically receives about 340 watts per meter square. The unit is ohmmeter, but it's watts per meter square. It measures intensity, and this intensity from the sun here, and this yellow arrow I would like you to pay attention, right, shows the absorption and reflection, right, of the incoming solar radiation from the sun by the Earth. Now, this red arrow on the other hand shows the radiation that's absorbed, right, by the Earth, but being re-emitted back as infrared radiation. And as you know, the infrared radiation has a long wavelength compared to the ultraviolet rays coming directly from the sun. That's of a shorter wavelength with a high frequency. Okay. So there's about 30% of this solar radiation that's reflected back to space, and we call this albedo. Okay. Now, the greenhouse gases in the atmosphere absorb some of this infrared radiation, right, that's emitted by the Earth's surface, right, and re-emits them. So it sends some of this energy back, right, and this warms the atmosphere, and that's why it causes what we call the greenhouse effect. Okay. Now, without the greenhouse gas, which means, right, there's a bit more, emissions of the heat upwards. But because the greenhouse gas, too much of it traps too much of the heat and it gets suspended here. Got it? Okay. Now let's turn it back because we are dealing with energy. We introduced to you this Stefan Boltzmann equation, two great scientists from Europe. This, as we know, regards the Earth, which is like a black body. In the previous slide, we talked about the Sun, the Earth, and Earth as a black body. This is a very physics term, like it can maintain a stable temperature by radiating the same amount of energy that it receives from the Sun, right? So in fact, it should be like a zero net energy balance. Now, when the greenhouse effect is enhanced, okay, right? Too much greenhouse gases, right? We talked about it just now, by anthropogenic emissions, right? Which means that the outgoing energy drop, and it causes the Earth energy balance to be positive momentarily, okay? Which means that we trap more heat, and that leads to a temperature rise. Now, because more energy will be radiated out, so according to this law, Stefan Boltzmann law, until the net energy balance is restored to zero, okay? Then the temperature of the Earth will stabilize at another increased level. So this Stefan Boltzmann effect acts like a negative feedback to keep the Earth's temperature from changing in one direction only. It should be equilibrium. But of course, we can reset the equilibrium to a high level. Think of it as another analogy. So, what assumption does it work on? Right, this Stefan Boltzmann distribution, this equation, it works on the assumption that the Earth is a perfect black body. Okay, but it's not. It's not a perfect black body. It has other internal mechanisms that regulate its climate in addition to the solar receipt, right, the energy from the sun, and its greenhouse effect. And some of these mechanisms are positive feedback that amplify the small perturbations. That's why we have increasing global temperature bit by bit, but now we want to keep it at a slower pace. Now suppose a slightly enhanced greenhouse effect increase the temperature only slightly, right, and this should stabilize, okay? So this may cause the whole total area covered by snow to decrease, right, okay? And this will lead to increased surface absorption of solar radiation, because now the snow, which is white, right, reflects more sunlight than anything else. When you have more glaciers, more white, right, then of course it's reflection of white color, like my shirt here, will emit more, radiate more light, reflected. Okay. So it's good to understand this Stefan Boltzmann equation and the law. You can read further about how more sunlight absorbed will cause the temperature to go up further and hence more melting, right, etc. Here, the equation is very simple. I stands for intensity. Intensity is measured by power per unit area. So just now you saw watts per unit area, which is per meter square. Now there's a constant here. We subsume and simplify into alpha, this just term, okay, the Stefan Boltzmann constant, this value here with the unit. T, capital T, represents the temperature in Kelvin here, so it's a power 4, right? So you can tell that the intensity of the radiations, right, is a function, a high function, the fourth power of temperature. So imagine if the global temperature increases, then you see what happens to the intensity and vice versa. Next part is the solar constant. I want to give you a bit of perspective that solar constant is just the average value, right? What it measures is some factors that affect this solar constant value are the presence of like the sunspots on the sun, right, the time of the day, location of the latitude, where you are, the state of the atmosphere. And the idea of the solar constant comes from a story that radiation traveling in space, right, in the outmost space, it carries the same amount of energy and has the same wavelength throughout when it leaves the sun's surface. But as the distance from the sun increases, right, it goes further from the sun, the radiation gets distributed over a larger area, right, because it radiates out, and thus affecting its intensity. Okay, so this relationship follows the inverse square law, right? And if you get the total solar emissivity value, okay, and then we divide it, okay, this value here, divide it by the area of an imaginary sphere, okay, like the Earth. Then in this case, you assume that the orbit of the Earth follows a perfect circular path with a radius of 1.5 times 10 power 11, okay? In terms of radius, remember formula is 4 pi r squared, right? Okay. And then using this formula, we can determine the mean solar constant of the Earth to be about 1361 watts per meter square. But that's assuming that the Earth, right, to be flat. But the Earth is not flat, okay? You know, the Galileo story. The Earth is not flat. So the Earth is roughly a sphere with a surface about 4 times larger than a flat disk. So you see, okay, 4 times. Pi r squared is the right area of a circle. So 4 times, okay. So we need to divide by 4 again, and hence we arrive at the value of 340 watts per meter square for the solar constant. Again, the derivation, no need to know, but I want to tell you a story about the background of the history of the solar constant and how do we get that if you see it in some news.